lecture about my research. So this is about this talk is about quantum algorithms for simulating open quantum systems. So I will first talk about the motivation of doing this. Why do we care about simulating quantum systems, and some basic background about open quantum. So what is open quantum system? What's the difference between open quantum systems and closed systems? And I will tell you some recent development of this line of research. Sorry about my voice. I'm sick around these days. So let's start. So when we talk about quantum computers, so what are the applications for the quantum computers? Let me see how I can hide this status bar. Let me see. Hide video panel. Okay. No, that's not this. No. Anyway. So um okay, so for if we have fault-tolerant quantum computers, we can of course break our cryptography schemes. For example, we can factor integers, and then we can break our password, and we can we can design quantum algorithms to sample from some probability distribution that is faster than classical algorithms. And we can also speed up scientific computations. For example, we have some quantum algorithms for machine learning and for the solving linear systems, which is much faster than classical algorithms. And another important implication is about simulating quantum dynamics. This is probably the most promising application if we have quantum computers, but because it's just not only because its importance, but also because it requires much fewer qubits. For example, if we have around 100 or a few hundred fault-tolerant qubits, then we probably can perform simulating tasks for some interesting systems. So what do we mean by simulating physical systems? We have a lot of motivation on the classical side. For example, when we design an airplane, we don't design it at the first place. We first build it like on the computer, and we first perform the computer simulation to test the airflow, if it can fly, and something like that. Then if it works well in the computer simulation, then we build the prototype, right? And for the circuit design, before we manufacture the chip or the circuit, we first run classical simulation to simulate the circuit dynamics, the circuit system. Classical circuit to test if everything is working properly. And also another application for simulating classical physics is probably it's video games, right? When you play video games, it's simulating physical systems. It simulates the movement of the players, simulates the movement of the balls. And we have enough motivation on the classical side, but we also have enough motivation for the quantum side. For example, we are interested in simulating the chemical reactions, biological processes, or more complicated, we are interested in simulating its photosynthesis processes. They are also these systems are the scales of the systems are too small, where the quantum effects takes into consideration. So classical physics simulation no longer works. So we have to use quantum. We have to consider quantum simulation algorithms. So if we have n qubits, and in general they can be entangled, so we use this 2 to the n amplitudes to mathematically describe the state of this n qubit system. And we send this n-qubit state to a system. For example, this can be some magnetic field or some laser beam, and we let the state evolve for evolution time t. Then we get some output state, output n-qubit state. So this is uh, the picture of a quantum system. We have some input state, and we just let it go under some evolution of some system. Then we have output state. So because in general the two-to-ten amplitudes, the n qubits are entangled. So they are so we have to use two-to-ten amplitudes to describe the state of the system. So how to keep track of the system. So we need exponentially many resources classically to keep track of the system state. So this is one evidence that this is hard for classical computers. And because we are simulating quantum systems, so we better use quantum computers to do the job. This is the famous quote from Feynman. And actually, simulating quantum systems is one of the first motivation Feynman proposed quantum computers in the early 80s. So, so what do we mean by simulating quantum systems? So now we have this quantum system, and we have some efficient description of this efficient description of this quantum system. So what we want is that we build a quantum circuit like this to mimic the behavior of this quantum system. For example, if we have the same input state, and then after the quantum circuit, we expect the output state of the quantum circuit is very close to the actual output state of the quantum system. So this should hold for all the inputs, all the possible input states. So if we can do this, then we see that we can simulate this quantum system for time t. So our task is to build this quantum circuit to do the job. So so now let me tell you two types of quantum systems. For the first type, it's called closed systems. So as the name suggests, this system is isolated from the environment. It just evolves on its own, and there's no dissipation of energy or no other energy coming into the system. So the dynamics of this system is described by this differential equation. It's called Schrödinger equation. So if you have this state, then the solution is defined by this operator e to the minus iht. So this h is called the Hamiltonian of the system. It describes the system, and if this h in general for a closed system, this Hamiltonian is Hermitian. So if h is Hermitian, this e to the minus iht is unitary. So you can see that's the solution. The evolution operator e to the minus iht is a unitary operator. So it maps a quantum state to another quantum state. Okay. But so this type of systems only exists in textbooks. So, but in the reality, every system is more or less is interacting with the environment. So when a system is interacting with the environment, then they have some exchange of energies. So or they have the system has dissipation of energies. So the system is no longer closed. and depending on depending on the strength of the interaction, the rate of uh, the environment, how fast the environment is evolving compared to the interaction. So we can further classify the open systems as Markovian open system or non-Markovian open systems. So let me first talk about Markovian open systems for now, and if we have time, I will talk briefly talk about non-Markovian open systems. So for Markovian open systems, this it's the evolution of the system is no longer governed by this Schrodinger equation, but it's more generalized master equation. For example, you can see the first term, the minus I times the commutator between H and rho. This is the general. This is just the Schrodinger equation in terms of this density operator. But we have other terms, these terms. So it's much more complicated than Schrodinger equation. And then the state is mixed state. It's no longer pure state. So for pure state, we can use a 2 to the n dimensional complex vector to describe it. But for mixed state, it's an ensemble of pure states, for example. Then we have to use this density matrix to describe a mixed state. For example, this is one specification, one description of the mixed state. We can describe it as an ensemble of pure states of phi j's. So this you can see this is matrix phi j phi j dagger. This is matrix, and we call this Link-Bradian. This super operator. This Link-Bradian. The super operator maps a matrix to a matrix. So this is called super operator. So this super operator is called the Link-Bradian. And the solution of this differential equation is described by this quantum channel. It's e to the L. So if you look at this, so one difference is that we have an I here, that we don't have an I here. And here this H is a matrix. It maps vectors to vectors. But here this L is a super operator. So the exponential of super operator can be defined by Taylor series. And this e to the LT, if you look at this, you look at this super operator, this generator, you can see that this is twisties. Okay, so that means if you see the form of e to the LT, this is completely positive and twist preserving. Excuse me. So this is the quantum channel. A quantum channel is a completely positive twist preserving map. So this is more generalized version of unitary matrices. So the difference between closed system and open system is that for closed systems, we use this Hamiltonian to describe the system. And the operator is a unitary matrix. But here, for open system, we use this more complicated generator, this Link-Bradian, to describe this system. And the generator is quantum channel. It maps mixed state to mixed state. It maps a matrix, density matrix to some other density matrices. Okay. So, but we have something in common here. So notice that for this closed system, we have this H. It's only acting on the system state, right? But for the open system, so intuitively, this open system involves many parties. We have the system, we have the environment, and we also have the interaction. So to describe a complete picture of this combined system, we need the system. We need to know the system Hamiltonian. We need to know the environment Hamiltonian. We also need to know the interaction Hamiltonian. But we certainly cannot handle this amount of information because this environment can be very large. So we certainly cannot uh, uh, have a description, have an efficient description of the environment. If the environment is very large, it might be beyond the capacity of quantum computers. So instead, we just use uh, some nice description. For example, if you look at this generator, it only involves operators on the system. Okay? It doesn't involve anything uh, on the environment because we only care about the evolution of the system. We don't care about the evolution of the environment, or we don't care about the something else. So we can just uh, derive something, some generator that only involves the uh, operators on the system. So fortunately for Markovian open systems, we can do this. We can get this efficient description using only operators on the systems. This is because we say the term Markovian, which the intuition is that the coupling, the interaction is not strong interaction. It's a weak interaction, and the system, the rate of the system, the dynamics of the environment is much faster. It's much faster than the interaction. So it means that whenever some information from the system is dissipated to the environment, it can be quickly washed out. Okay, so the information from the system to the environment can be quickly washed out without the information coming back to the system again. So this is the one-way flow of information. So this is called Markovian system. So if we have this system, we're in a relatively nice situation where we can have this generator that only only has the operators acting on the system. So let's take a closer look at this generator. Okay, so this is the Lagrangian. This is the solution. Okay, and we call this the Lagrangian. So this part is Hamiltonian part. This part is we call it jump terms. We call this each L. We call each L the jump operators. And we call this evolution the Lagrangian evolution. So because this Lagrangian is traceless, so this is a completely positive trace preserving map. So let me give you some examples of this Markovian open systems, or in other words, the Lagrangian evolution. So let's consider this Lagrangian equation. So for this Lagrangian equation, we don't have this H part. We don't have this Hamiltonian part. And we have only one jump operator. It's very simple, defined by this 0, 1, 0, 0. And we can, for this simple case, we can work out the closed form expression for the cross operators for this channel. Okay, so for this channel, the channel has these two cross operators A0 and A1. So they are in this form. And if you plot the state in the block sphere, you can see that, okay, suppose this green arrow is the initial state, then it will just evolve closely, slowly to this cat0 state. So if you are familiar with this, you might recall that this is just the continuous time version of amplitude damping process. Okay, if you have an amplitude damping if you have amplitude damping channel, the state is instantaneously snaps to this K0 state. But if you consider the continuous time version, it's just slowly goes here. It's a continuous time process. So the difference between here I use another block sphere to demonstrate the difference between this open system and the closed system. For Hamiltonian evolution, the state will be always a pure state, right? So it's just the state is always on the surface of the block sphere. So it's just the rotating. Okay? But here for the open system, the state becomes a mixed state. So it goes inside the block sphere and it converges to some fixed point. So the speed and direction of the evolution changes. But for the Hamiltonian evolution, it's constant speed rotation, okay? And the state is always pure state. And here are more examples of Lindblad evolution. So this is depolarizing process. So combined with some Hamiltonian. If you just have a depolarizing process without any Hamiltonian, this will be a straight line from the state to the center of the block sphere. So if you recall the depolarizing channel, it maps everything to a completely mixed state, which is the center of the block sphere, right? But if you consider the continuous time version, the depolarizing process, it's just it's continuous time version, continuous time evolution from the pure state to the maximum mixed state. But if you combine with some Hamiltonian, you have this interesting spiral trajectory like this. So actually, this continuous time depolarizing channel describes the error model of quantum circuit. It's so we believe we think in general or in most cases the model the error model of quantum circuit is a depolarizing channel, okay? But the rate is very small. So if you apply this the error model, if error model can be viewed as some open system, if you evolve this error model for a small time, it just only goes inside the block sphere for a small amount of distance. So for this picture is another combination. This is the amplitude damping process combined with some Hamiltonian. So recall that if you have just the purely amplitude damping process, it's just like this. But if you combine this process with some Hamiltonian just rotating in this way, you get this trajectory. Okay? And eventually it will converge to some fixed point. Now, okay, so it seems very physicsy here, but why do we care about this simulating systems in computer science? Right? So we have many motivations. So for example, we have a lot of applications for simulating closed systems. For example, we have the Hamiltonian simulation can be used as an important subroutine for the HHL algorithm, and it can also be used as subroutines for other quantum machine learning algorithms. And we also have a lot of applications for simulating open systems. For example, we can prepare Gibbs state by simulating open systems. And by studying this open system, we can understand the error model of quantum circuit. Just as I said, this error model is described by this depolarizing process. And also we can use optimization to we can do optimization by simulating open systems. There is a recent paper by Yang and other authors. So they showed that you can optimize, you can perform some convex optimization by simulating some special open quantum systems. Okay. Now, let's talk about the simulation algorithms for Markovian open systems. So, okay, so now I'll give you a simple warm-up example of this algorithm. So now let's suppose that this Lagrangian can be decomposed as a sum of local terms, where each term is only acting on a constant number of qubits. So each term, the evolution for each term can be efficiently implemented. Okay, then we have this trotter like decomposition. So if we have a very small evolution time delta, so e to the L delta, this delta times evolution can be decomposed as the product of the evolution operator for each term. But you have this little error here, because the different L's, the different terms don't commute. So this is not exactly equality. So you have some small error, delta squared. So the idea is that you pick a small evolution time, you just use each individual evolution to simulate the product of this operator of the channel. Then you just repeat it many times for evolution time t. For example, for evolution time t, you can choose a large R, so that t over R is very small. Okay, then you just repeat this R times. Then you will have these total errors t squared over R. So if you force this total error to be epsilon, then you can choose this R to be t squared or over epsilon. So this is the total complexity of this algorithm, of this simulating algorithm. It's t squared over epsilon. So it has a superlinear dependence on evolution time t, and it also has a polynomial dependence on 1 over epsilon. Okay, so this algorithm is very simple, and it does not have this optimal performance. So for each term, for example, for each term you can use Stein spring dilation to implement this term, the operation on this term. Okay. And there's actually a limitation of approaches like this, where you use Stein spring dilation to implement each term. So I'll demonstrate this limitation. So if we consider a large enough Hilbert space, then every open system becomes unitary evolution. So we can just reduce this Lindblad evolution to Hamiltonian simulation in a larger space. Okay? For example, if we consider the amplitude damping process, so we have only one jump operator, and then we can come up with this Stein spring dilation Hamiltonian looking like this. And then instead of okay, now then the goal is to simulate this channel, right? But what we do is that we just simulate this larger Hamiltonian for time tau on this initial state. This initial state is we have this additional ancillars initialized to 0, and we just simulate this Hamiltonian evolution for time tau. So this is what we do, and then we trace out the environment. We get the reduced state, system state. So this is what we do in this framework, and this is what we want. So we want to compare this t with tau. Okay. So we can see that when the initial state is in this form, then if you work, there's a closed form expression for this channel. It's written in this, and you can also work out the closed form expression for this channel. It's like this. So basically, you can just compare 1 minus e to the minus t and sine squared tau. And when t and tau are very small, then we have that by a series of deductions, we can conclude that this tau should be very much larger than t. More specifically, this tau should be at least square root of t. Okay, that means if we can consider a very short evolution time, if we just want to simulate the evolution for time t, but what we paid for this Hamiltonian simulation is the cost is much bigger. So this tau is actually square root of t. It's much bigger than t when t is very small. Okay, so right. So this demonstrates that if we just use this framework and we just simulate this, we use the Stein-Spree dilation to simulate the very short time evolution, we need to pay much more than what we need. Okay. This could be that we just picked a very bad Hamiltonian. Is it possible that there are other Hamiltonians where we get a better time dependence? It turns out not. It's not the case because we can come up with a lower bound. We have some special case. So for example, if we consider this discrete discrete process to simulate a continuous process, we just continually reset the ancillas, okay, and we just use a larger Hamiltonian. We continually reset the ancillas, and then we just keep this system state to evolve. So let's see how what's the lower bound for this type of simulation. It turns out that for each Hamiltonian evolution, if we have this initial state and we trace out this ancillas, it can be approximated by this local Hamiltonian approximation. Okay, and for this local Hamiltonian evolution, it does nothing on the ancilla, and this error is only delta squared. Now, suppose this continuously reset model is what we do here for the simulation algorithm, and this is our target evolution. And it turns out that we can use local Hamiltonian approximation to approximate this our simulation algorithm, and the error is r delta squared because we repeated r times, and for each time it introduced error delta squared. And the distance between this and this. And there are some special examples. There are some special Lindbladian. For example, the completely depolarizing channel. Okay, if it evolves for constant time, the channel will map some pure state to a complete mixed state. But if we just use this local Hamiltonian approximation to approximate this, because it's a local Hamiltonian approximation, so the pure state stays pure state. So distance between the two is 1/2 for this special example. And we want this our simulation algorithm to be the distance to be small. So even if the simulation error is constant, so by triangle inequality, we need this to be large. It means the delta, the time interval should be at least square root of 1/r. So if we consider total Hamiltonian evolution time, because delta is square root of t over r, and we have r pieces, so total Hamiltonian evolution time is square root tr. So if you want a you want a larger r to make the simulation process more and more precise, but you have a larger and larger R, the cost will blow up. So, but what we actually expect is that if the cost scales as this T over R, so it doesn't depend on R. This is what we want. But in reality, if we use this larger Hilbert space to simulate this is the cost. So for example, we can choose this R to be T squared over epsilon. So for this we'll achieve this T to the 1.5 over square root of epsilon. So you can see that this dependence is still super linear in evolution time t, and it's polynomial in 1 over epsilon. So it's still not as desired. Okay, so we want to achieve this linear dependence on time t and the polylog dependence on epsilon. So we have to use some other advanced techniques. So to talk about this advanced techniques, let me introduce this algorithmic tool called linear combination of unitaries for channels. Okay, suppose we're trying to implement this quantum channel that maps this row to this. This channel is specified by the cross operators AJ, where each AJ is specified by this linear combination of unitaries. Okay, so we know the implementation of the U's, we know the coefficients of betas. Now, how can we implement this channel? And we use this circuit. So this controlled B will prepare the amplitudes, and this controlled U will just it determines which UJK is acting on the system depending on the this J register and the K register here. And after that, we uncompute this B gate. And after the circuit, if we trace out, discard the first two registers, then the third register will contain the state with certain success probability. Okay, the certain success probability depends on the sums of these coefficients. So, and it can be boosted using amplitude amplification, for example. Now we use these techniques to simulate linear random evolution. So I first introduced this first order approach. For this first order approach, we want to use first order approximation to approximate this delta time evolution as a quantum channel using cross operators. And each cross operator, if each cross operator can be written as a linear combination of unitaries, then we can use our previous approach. We can use this circuit to implement this, right? So recall this is the Lagrangian, and we consider this instantaneous approximation map. So when delta is very small, and we want to approximate this e to the delta evolution using this cross operator, it turns out that the cross operators are in this form. Okay, so the A0 is this, A1 is this. So if L is a linear combination of unitary, so this AJ is a linear combination of unitary, and if H is also a linear combination of unitary, then this A0 is also a linear combination of unitary. Now all the cross operators are linear combination of unitaries. Then we can use the algorithmic tool to implement this linear combination of unitary. Okay? It turns out that the error of this approximation is 1 over R. So you can choose a large R to make this error small. So you use this, and you come up with this LCUs, linear combination of unitaries for each cross operators. And this sum of SJs, each SJ is sum of the coefficients betas for AJ. So the success probability depends on the sum of SJ squared. It turns out that the success probability is something like 1 over 1 minus R. Sorry, 1 minus 1 over R. Okay, then you can just repeat this R times to make this success probability constant. Then you can use if you repeat this R times, you make the success probability constant, then you can use one shot, and further you can make this constant 1/4. Then you can just use one shot of amplitude amplification to boost the success probability to 1. Now you just use these R times. Now success probability can be adjusted to 1/4. Then you use amplitude amplification to make this perfect. But the cost is R, right? So you need this R to be 1 over epsilon. So this R, the cost is R, but so this is too bad because the error dependence is like something like 1 over epsilon. We want to achieve polylog of 1 over epsilon. So we need to do something to reduce this cost R. So if we look at these operations, the controlled Bs, okay, it turns out that if we consider the R-fold tensor of controlled Bs, okay, so the most amplitudes will be concentrated to this 0, 0. And if we have this 0, 0, the corresponding unitary U will be identity. So okay, identity means doing nothing. It means for the majority of this amplitude, this U will do nothing. So we can use this compression scheme. We can compress the state. We can compress state to a state with use this polylog 1 over epsilon factors of non-0, 0 state, and it's only cost error epsilon. Now we can reduce the error from 1 over epsilon to polylog 1 over epsilon. Okay. So this is the first order approach. Let's see that this works. We achieved linear time dependence and polylog dependence on this 1 over epsilon. Okay? This is great, but the only thing not aesthetically satisfied is this. We use this this compressed scheme, so which is much involved. So we want to get some simple approach. So now we consider the higher order series approach for simulating this Lindblad evolution or the Markovian open systems. So the goal is to get rid of the compression scheme. So, so if you are familiar with this techniques for Hamiltonian simulation, you probably notice that you can simulate Hamiltonian evolution by Taylor series. Okay? So, for example, you can approximate this evolution operator by this truncated Taylor series. You truncate it to order k, and it turns out that this k doesn't need to be too large because the Taylor series converges very fast. Okay? Now, if H is a linear combination of unitary, then you can see that this summation, this Taylor series, truncated Taylor series, is also a linear combination of unitary. So you can just directly use the linear combination of the unitary circuit to implement this approximation, and it's very efficient. But now we want to use this similar idea for this Lindbladian, but it turns out that it's very challenging because the nice thing about the Hamiltonian is that if you just consider higher orders of Hamiltonians, it's still a linear combination of unitaries, right? But here for this higher powers of Lindbladian, we don't know how to keep track of this completely positive structure. For example, if we consider the second power of Lindbladian, it's already messy enough. So that we cannot keep track of the completely positive structure. So we want to use this structure, this cross operators. So this is good. L squared, L dagger squared. This is good. Okay, this is not good. So on the left-hand side, we have L dagger L, but on the right-hand side, we have L dagger. So this is not completely positive map. So the thing is, the challenge is that we don't know how to keep track of this, the complete positive structure of higher powers of this Lindbladians. So we cannot directly use Taylor series to do this. Okay. So so we have to use some more complicated techniques. This is based on Duhamel's principle. Duhamel's principle is commonly used tool in mathematics, in applied mathematics to solve differential equations. So to use this, we first decompose the Lindbladian as the drift part. Sorry, this jump part. This drift part is like this, and the Lj's jump part like this. So this J it's called effective Hamiltonian. It's defined by this. So this is not Hermitian. So the L can be decomposed as drift part and the jump part, and then we apply this Duhamel's principle iteratively. It turns out that the evolution for time t can be written as the evolution for the drift part, okay, plus this state, okay. So this might look scary, but okay. But let me tell you that you can basically ignore this third term, because this is a higher dimensional integral. This is integral in a higher dimension, integral of the corner in a higher dimension. Okay, so this is very small, so you can basically discard this with little error. And also for the second term, you can see that e to the LD, because of this form, e to the LD is a completely positive, and this LJ is completely positive. So everything is completely positive. So the integrand is a composition of completely positive maps. And we just need to deal with these integrals, and we can use some other. We can use Gaussian quadrature to approximate the integrals by summations. Then we can basically approximate this by the desired form of this integrals. So we can use the algorithm tools. In other words, the linear combination of unities for channels to simulate this map, and we can achieve the total complexity t times polylog t over epsilon. So this has the same complexity with the first order approach, but it's conceptually simpler. It doesn't require any compression scheme. Okay. Now let's briefly talk about this non-Markovian open systems. So if we consider this system where the system evolution is described by this differential equation, where this H total, the total Hamiltonian is this, like this. We have a system Hamiltonian, we have a band Hamiltonian. This is the identity, okay? And then we have some interaction terms, S and B. S is acting on the system, B is acting on the band. So this M cannot be too large. This M should be small, and we assume the initial state is the initial state of system and the bath are separated. Okay, so we assume that the initial state of the bath is a thermal state of the bath, and we have some arbitrary initial state for the system. And this lambda is called coupling operator. So in the regime of the lambda, it's much smaller than 1. And if the dynamics of the bath occurs at a much faster rate than the system, then as I said before, this is called Markovian system, open system, okay, this is what we talk about in the previous part of the talk. And we still need this lambda to be very small, this coupling to be very small. But when the bath dynamics is comparable to the system dynamics, then this is non-Markovian, okay? And this is something we can deal with. But if the coupling operator is too large, we don't know how to deal with this type of non-Markovian systems. Okay, so to deal with this case, we need more information. Again, so the goal is still we come up with some nice master equation that involves only the operators on the system. But for this case, it's we kind of need more information from this correlation between the from the interaction. For example, we need this correlation, the Bethe correlation function. We need this information. So okay, the Bethe correlation function can be defined by this way, can be defined by this. You have the thetas, Q case. This case shouldn't be large, case small, and this D case, and the Q case is some real vector. We need these vectors, and it turns out that if we have this additional information, we can embed the system into a larger system, okay, and we can get the master equation for this larger system is described by this differential equation, okay. So this looks much similar to the Lindblad case, but we don't have this some other terms. We were missing some terms, but we can still use the techniques for simulating Lindblad evolution to simulate this master equation. So now this H and K involves this DKHS, something like this. Okay. Okay, so there shouldn't be TK. Sorry, there shouldn't be TK here. This is a typo. Okay. This H and VKs involves something we know. Okay. So basically, given some information, given some description of the this HS and this S alpha, we only need the something acting on the system, HS and S alpha, and we need the information of the Bethe correlation function so we can simulate this dynamics. The dimension is only, so this is, sorry, not if, sorry, this is another typo. The dimension is enlarged by the factor of K. It's because we enlarge the dimension of the system, right? So but it's not large by much, it's large by factor K, and the target state is in the first block of this gamma. And then we can use previously mentioned techniques to simulate this evolution, to simulate some non-Markovian open systems. So this is end of the talk, and thank you so much for your attention. I'm happy to answer any questions. Thank you so much.